Paper 2 from May 22, Timezone 2. Starting off with balancing equation, where we have lithium to become lithium hydroxide by dissolving in water. Simple balancing equation. We're going to start off with 2 lithium hydroxide to make sure that we've got 2 water. We can have 2 water on the reactant side, meaning that we will need to supply 2 lithium and we'll end up with 1 hydrogen. We're given the mass of lithium as 0.2 grams. We need to find the molar concentration of lithium hydroxide. For that, we need to find what? The amount of lithium hydroxide in mole, and then divide that by the volume of water given. To find the amount of lithium hydroxide, we have to find the amount of lithium. Why? Because the molar ratio of lithium and lithium hydroxide is 2 to 2. 2 to 2, 1 to 1. Amount of lithium is going to equal to the mass of lithium as given by 0.2 grams over the RAM of lithium. What's the RAM of lithium? Look up on your periodic table and it will be given as 6.94 grams per mole. Let's do the math and we'll be given 0.0288 mole. Amount of lithium we have is 0.0288 as well as the amount of lithium hydroxide. Now, this much lithium hydroxide is in how much water? 0.5 dm cube. And this will give us the concentration as 0.0576 mole per dm cube. Our answer. We're then going to calculate the volume of hydrogen produced at specific temperature, pressure. What are we talking about? We're talking about usage of ideal gas equation, PV equals nRT. For that, we will need to work out the mole of hydrogen produced because the rest of the data we already know. What's the amount of hydrogen produced? Well, we're going to go back to the balanced equation. We have inputted 0.0288 mole of lithium and we will output half that amount because 2 to 1 molar ratio of lithium to hydrogen. 0.0144 is the amount of hydrogen that we know of. So let's put the values into the rearranged ideal gas equation. We're trying to find the volume. So volume equals nRT over P, which would equal to 0.0144 mole times R, gas constant. Look up on your data booklet, 8.31 joules per Kelvin per mole is the answer, times temperature. We are given 22.5 degrees Celsius. Do you put that value in? No, you don't. You have to convert that value to Kelvin, which would then be 273 plus 22.5, which would be 295.5 over pressure. Pressure we're given as 103 kilopascals. But let's convert that into Pascal. So we are given 103,000 Pascal. Now, this should give us the volume in the unit of meter cube. Why? Because that's the standard unit for volume utilized in PV equals nRT, provided we have used Pascal for pressure, not kilopascal. Do the math, and we'll be given 0.00343 meter cube. We can convert that into what value? cm cube. We are asked to put the value in cm cube unit, which would convert to 0.343 dm cube, and then 343 cm cube. Hydrogen gas volume collected, we theoretically postulated that to be 343 cm cube, but in reality, the actual volume produced was less than that. I can think of two reasons for that. First, we have used impure lithium sample. What does that mean? That means that the actual amount of lithium used that has reacted was not 0.0288, was not this value, but instead lower. And that would also affect the amount of hydrogen produced to be less than 0.0144 mole. I can think of another reason as loss of product. Maybe we have not successfully captured the hydrogen produced. Could be an answer. Maybe hydrogen gas has been used in combustion. Hydrogen can combust because we've got energy released from the reaction of lithium and water. It's an exothermic process. Energy released with ample amount of oxygen around hydrogen could lead to hydrogen combustion. So hydrogen volume used up. We have change in oxidation state of lithium, don't we? We go from 0 to +1 oxidation state. What that means is lithium has been oxidized by an oxidizing agent, and that oxidizing agent is going to be water. Why? Because water is in turn reduced by the reducing agent lithium. Water is reduced to H+. Water has been reduced to H+, where hydrogen of water has gained. Specifically speaking, it's the H+ of water has gained electrons to become reduced to hydrogen gas. I have previously mentioned that lithium with water reaction is exothermic. Well, the simplest physical observation we can make out is measure the temperature increase. Temperature rise can be measured by thermometer usage. What else can we think of? Well, think of the lithium, the lump of lithium floating on water surface. Maybe that lump may catch fire because there's heat being produced. Lithium lump catches fire. What other potential physical observations could we make? You could go with what I've just mentioned about hydrogen combusting, and that will create the pop sound. The pop sound that arises from that is hydrogen, the product, combusting. Pop sound from hydrogen combustion. Calcium having a higher ionization energy than potassium means that the electrostatic attraction between the nucleus of calcium and the valence electron, the electron being ionized, is stronger. And what are the reasons for that? It's because the nuclear charge, the effective nuclear charge of calcium is greater than potassium. There are more protons in calcium, isn't there? So the first point we're going to make is that the nuclear charge of calcium is greater. What other reasons could there be behind electrostatic attraction between nucleus and valence electron being greater? What if the distance between the nucleus and the valence electron is shorter? And that is actually true because calcium is smaller than potassium. Smaller atomic radius. Remember, how does the atomic radius change across the period? Decreases across the period. And this is why across the period, the ionization energy has a general trend of increasing. We have the energy levels of a hydrogen atom with the discrete levels converging towards high frequency, high energy, where n equals infinity represents the highest possible energy level. Two limitations to this model of electron energy levels is that, well, we know there are now sublevels, orbitals, that represent the position of electrons, and that's the more accurate version of atomic substructure. Therefore, we're going to say firstly that the model does not represent atomic orbitals that we would expect. Second, this model only applies to hydrogen with one electron, atom with only one electron. Only applies to atoms with one electron, and that's hydrogen. Electron transition for the ionization of hydrogen atom in the ground state would be an arrow starting from n equals 1, the ground state, all the way to n equals infinity. That would represent ionization energy. Electron transition in the visible spectrum means we have relaxation of an excited electron from n equals 3 or higher to n equals 2. And we are talking about the lowest electron transition. I'm going to color this in a different color. Any of the following relaxations could correspond to visible wavelength. However, we are interested in the lowest energy, which would be the red color. The highest energy visible wavelength would be violet, and that probably would be n equals 6 to n equals 2. So what we're interested in is n equals 3 to n equals 2. That would have the lowest energy gap corresponding to the red wavelength of the visible spectrum. Catalysts provide an alternate reaction pathway with a lower activation energy, and in doing so, the rate of reaction is increased. That's how we're going to answer the question. Provides alternate reaction pathway. And this alternate reaction pathway has lower activation energy, thereby decreases reaction rate. We're not going to mention this in this question, but for equilibrium, for reversible reaction, catalyst. Oh, did I just say decrease reaction rate? That's so stupid. It's increases. Apologies. Increases. Reversible reaction, there is the forward and backward reaction occurring simultaneously. Catalyst affects both reactions. Maxwell-Boltzmann distribution curve. X-axis is kinetic energy. Kinetic energy. Y-axis is going to be number of particles. Number of particles. The standard distribution curve that we draw is going to have this shape. Maybe I've drawn the finish line to be too high. I'm going to reduce that down slightly. Now let's label this as T1. We are going to draw T2, where T2 is at higher temperature. I'm going to make sure that both T1 and T2 starts at the origin. The lower temperature T1 will peak at lower kinetic energy, but the higher temperature T2 will finish higher than T2, like that. So I'm not very happy with this diagram. I'm going to make sure that we're near 0 for both T1 and T2. Okay. Hopefully what you draw is a smoother curve than mine. Temperature increase will be counteracted by the system favoring the backward endothermic, the endothermic backward reaction. That means the position of equilibrium, POE, shifts to the reactant side, meaning the percentage yield of SO3 product decreases. Temp increase counteracted by system, equilibrium system favoring. Here's the key term, endothermic backward reaction. Yes, to be able to answer questions like these, we have to be given the information of the forward reaction enthalpy change value. We don't need the specific value, but we need to know if it's positive or negative. Endothermic backward reaction. As a result, the position of equilibrium shifts to the reactant side. If you don't write what I'm about to say now, you're only going to get 1 mark, because after all, we have to state the effect that SO3 percentage yield decreases. Well, let's add water to SO3 to form H2SO4, sulfuric acid, easy. A bit of illusion, a bit of digression to acids and bases topic. Factories produce sulfur dioxides. Sulfur dioxides combine with oxygen to become sulfur trioxide, and sulfur trioxide in the atmosphere will dissolve in water vapors, leading to acid deposition. Sulfuric acid falling down. Meaning of strong Bronsted-Lowry acid is proton donor that completely dissociates, like HCl. Like sulfuric acid, like nitric acid. Besides sulfuric acid, nitric acid is also a strong acid. We can draw the Lewis structure of nitric acid because it's the protonated form of the nitrate ion. So let's start by drawing the Lewis structure of the nitrate ion, which would have nitrogen at the center. that is double covalent bonded to one oxygen and single covalent bonded to two negative oxygens. And why is that? That's because the negative oxygen, the two negative oxygens have -1 formal charges, having 3 lone pairs each, whereas the double bonded oxygen only has 2 lone pairs. We also should acknowledge how the formal charge of the two single covalent bonded oxygens are -1s each, but for nitrogen, single plus. This is described as trigonoplanar, and this trigonoplanar is the first key phrase we will use to describe the electron domain geometry of nitrate. Trigonoplanar geometry with 120 degrees bond angle between the nitrogen to oxygen bonds, and they are located as far apart from each other as possible. This is how I would explain the electron domain geometry of nitrate ion. Trigonoplanar, bond angle, and acknowledge via CPI theory that the bonds are located as far apart from each other as possible to minimize repulsion. Allotropes of carbons include what? Diamond, graphite, and Buckminster fluorine, C60. We're going to look at C60 and diamond, especially their comparison and contrast. Differences between the bonding of carbon atoms in C60 and diamond. Okay, we would be acknowledging how in C60 each carbon is bonded to 3 adjacent carbon atoms, whereas in diamond each carbon is bonded to 4 adjacent carbons. At almost 120 degrees. Why? Because it's almost trigonoplanar. Not completely, but almost trigonoplanar. So the bond angle is not going to be, it's going to be less than 120, but it's going to be between 109 and 120 degree bond angle. But for diamond, specifically, exactly at 109.5 degrees. For C60, also the bond angle is between 109.5 and 120. For H levels, we can go beyond. We can give more differences to suggest that each carbon is bonded, but also each carbon that is sp2 hybridized is bonded to 3 adjacent carbons. Each carbon atom that is sp3 hybridized is bonded to 4 adjacent carbon in diamond. Is there anything else we can say? We can maybe say that electrons are delocalized partially across the carbons of C60, while in diamond there's no delocalization of electrons. But that's pretty much it. Diamond sublime at higher temperature definitely than C60. Why? Because it's a giant covalent macromolecule. Diamond sublimes at higher temperature than C60 because of its giant covalent macromolecular nature compared to how C60 is not a simple covalent molecule, but it's quite complex, but it's a molecule that have intermolecular forces to compared to how C60 molecules have intermolecular forces, primarily London dispersion forces, LDF. State two features showing that propane and butane are members of the same homologous series. Members of the same homologous series have the same functional group and therefore the same general formula. And also because they differ by repeating units of CH2, they will have a general formula. They will have similar chemical properties and similar physical properties as well, but gradually differing physical properties with increasing carbon numbers. So we want to say that members would have the same general formula of what? What's the general formula of alkanes? CnH2n plus 2 would be the general formula, as well as members differing by repeating units of CH2. Similar chemical properties. They undergo similar reaction mechanisms like free radical substitution reaction. We'll skip this question as we have the mass spectrum data removed for copyright reasons. Presence of carbon to carbon double bonds, in other words alkenes, undergo the characteristic electrophilic addition reaction with halogens and other electrophiles. So therefore, bromine water testing could help us identify, could indicate the presence of carbon double carbon bonds. So if there is, we would have bromine water with the orange-brown color decolorizing. Why? Because as the halogen is, the bromine halogen, as it is electrophilically added to our carbon-to-carbon double bond, we're losing halogen identity. Halogen are integrated into our new halogenal alkane molecule. Therefore, double bond is lost, but the halogen is also lost. So the characteristic orange-brown color is lost as well. Butene is drawn, can be drawn as follow. Obviously, we can also draw butene as follow as well. For the HO purpose, we want to acknowledge how there's the Z annotation given at the beginning of butene, which is asking us to draw, to pick out the structural isomer with the two methyl substituent groups to be on the same side. So we want the first structural formula that we have drawn. But for the SL level, we don't need to know what Z stands for. Therefore, both drawings could work. But2-ene can be represented in condensed structural formula as CH3, CH, CH, CH3, where there would be the double bond between the second and the third carbon, plus hydrogen bromide, which would lead to the hydrogen bromide being integrated into our but2-ene to become CH2, CH, Br, CH3. And we refer to this reaction as electrophilic addition. Easy question. Too easy. Actually, I'm going to regret that. I'm going to regret what I've just said about being too easy. We are having to compare NMR spectrum of but2-ene and bromobutane without the spectrum given. Okay, this is quite difficult. So let's draw out the hydrogen environments of but2-ene and 2-bromobutane. Let's go with but2-ene. What are the hydrogen environments here? We've got, firstly, symmetrical molecule, which means that we've got 6 hydrogens that occupy the same hydrogen environment. We've got 2 hydrogens that occupy another hydrogen environment. Now this will compare with 2-bromobutane, our product, where firstly there are more hydrogens, and we've got more distinct hydrogen environments as well. First hydrogen environment would be closest to the bromine. Second hydrogen environment would be the CH3 that is bonded to CHBr. Now there's the third hydrogen environment that is bonded to CHBr as well as CH3. The CH2 hydrogen environment is bonded to the CHBr environment on the right, and at the same time CH3 environment on the left, which is the final hydrogen environment. There are 4 different hydrogen environments in our 2-bromobutane. Okay, so how do we answer this? But2-ene will compare and contrast with 2-bromobutane. Firstly, with number of peaks, 2 versus 4. There will be further discrepancies of ratio of hydrogen atoms or peak intensities. We will have 6:2 ratio. We'll have 6:2 ratio for our but2-ene. However, for our 2-bromobutane, we will have 3:2:1 and 3 ratio. 3:2:1:3. Now, that's all we need to know for SL level, but for higher level we can go further to contrast the two spectrum. We could talk about chemical shifts. What is the characteristic hydrogen environment of butene? Well, I do see a double bond. Therefore, the double bond is going to be our characteristic hydrogen environment, and that is illustrated by 4.5 to 6.0 ppm chemical shift. What about 2-bromobutane? Well, we have a halogen right there. Therefore, the hydrogen that is bonded to halogen bonded carbon right here, 3.5 to 4.5 will be our characteristic. (3.5 to 4.5 ppm will be our characteristic hydrogen environment. There will be a peak at the two characteristic hydrogen environments for the two molecules. Now, the final contrast point, splitting patterns. We can also compare and contrast the splitting patterns for the two. Again, butene is quite straightforward. We have the CH3 bonded to the adjacent carbon with one hydrogen attached. And what does that tell us? It tells us that the CH3 will be a doublet. The CH3 will have a doublet peak, while the CH hydrogen environment will have a quartet. The CH hydrogen is adjacent to a carbon with 3 hydrogens, and therefore 3 plus 1, a quartet. Let's move to the final hurdle, 2-bromobutane splitting patterns. Starting off with CH3 in red. CH3 in red is bonded to CH2. 2 plus 1, a triplet. Difficult, very difficult. CH2 is bonded to CH3 on the left. Now that's 3 hydrogens. But not only is it bonded to CH3, but it's also bonded to CHBr. Now, it's bonded to 2 carbons that in total are bonded to 4 hydrogens. That's 4 plus 1. I think it's quintet. If we use the Roman numeral, it should be quintet, but let's just call it multiplet. Next up, hydrogen. The single hydrogen, again, is bonded to CH2 on the left, CH3 on the right. In total, 5 hydrogens, 6. 5 plus 6. Latin numeral is sextet. But again, let's call it multiplet. Finally, CH3 in orange is bonded to a CHBr. The adjacent carbon has only 1 hydrogen attached, which means that we will end up with a doublet splitting. Okay. We've gone through way too much info for a 2 marker. Go with the easy 2. Save yourself some time. What reaction is this? Methane is reacting with chlorine to become chloromethane. That's free radical substitution reaction. We need UV light to supply the energy to initially create the chlorine free radical. And we're going to look at the energetics of this reaction. Section 11 tells us that we will be using bond enthalpy values, where we will be breaking 4 CH bonds, 1 Cl to Cl, and we'll be forming 3 CH and 1 CCl, and finally 1 HCl. Enthalpy change delta H is going to equal to sum of the bond enthalpies of our reactants. Why? Because we need to input the energy that corresponds to the bond enthalpy values of our reactants to break them. And we represent this as what? Sum of bonds broken. We'll be subtracting sum of the bonds formed. Why? Because the new bonds formed will be releasing energy, and that will take negative sign. Let's go to our section 11 to look at bond enthalpy values, starting off with CH having 414, ClCl having 242. So 414 times 4 plus 242, nice numbers, take away 414 times 3 plus CCl. What is the bond enthalpy for CCl? 324. 324. And we need to take away again HCl. What is HCl? HCl. Sorry, that's not HCl. HCl is 431. 431. Let's just make sure that we have counted correctly. In methane, there are 4 CHs. In Cl2, there's 1 Cl to Cl. In CH3Cl, there are 3 CH, 1 C to Cl, HCl, H to Cl. We have not left out anything. If we do the math correctly, we'll end up with a kilojoules per. We'll end up with kilojoules value, which would be minus 99 kilojoules. And we can draw an energy profile diagram for our free radical substitution reaction, where we know, being an exothermic reaction, we will have, let's draw the enthalpy of reactants at a higher value, being an exothermic one. We will have the reactants, that's what? Methane and chlorine. And we will have also the products, which is what? Chloromethane and hydrogen chloride. We will have delta H value. That corresponds to the value we have calculated as minus 99 kilojoules. Not displayed, but we can also speculate how there will be the transition state as well as the activation energy. Electrolytic cell of molten zinc chloride. at 450 degrees Celsius. Why so high temperature? Well, we do need to melt our electrolyte, zinc chloride. And zinc chloride is what? An ionic compound. And ionic compounds in general require high temperature for melting. 450, we have molten zinc 2+ and Cl- ions that will be migrating to cathode and anode respectively. Cathode will be attracting our zinc 2+ ions. Zinc 2+ liquid will be gaining electrons, specifically 2 electrons, to become zinc liquid. That one I'm not so sure. Why? Because zinc will have quite a high melting point, being a metal, and due to the nature of metallic bonding, zinc is likely to be a solid if the melting point is higher than 450. We do need to check that, and let's check that by going to melting points and boiling points of the elements. I do see zinc to have 419.5 degrees Celsius melting point, which is lower than our electrolytic cell temperature. Therefore, it will be molten and therefore liquid state. We don't need to be concerned about chlorine because chlorine will be oxidized. Chloride ion will be oxidized into chlorine gas without any doubt. Using the two reduction oxidation half equations we have just derived, we can formulate the full redox reaction, the full redox equation by simultaneously adding the two half equations. Now let's add the two to derive zinc 2+, 2Cl-, but together they will actually ionically attract each other to become zinc chloride liquid. So let's represent zinc chloride to zinc Cl2 liquid, turning into zinc liquid and Cl2 gas. That's the equation that represents our electrolysis. Now, we were given the guidance of using section 7 of the data booklet. We have just used that in our previous answer, just to make sure that the zinc produced would be in liquid state.